Today I will be giving a lecture on balancing of rotating masses. There are so many, I will just write the title. Balancing of rotating masses. There are so many examples for rotating masses. Examples of rotating masses are number 1, ceiling fan. Number 2, household pump. Mixie, grinder, and these are all household equipments. The industrial are number 1, steam turbine. Number 6, gas turbine. Number 7, propeller of aeroplane. Propeller of aircraft, etc. And so like this, so many examples of rotating masses are there. In automobiles, the example is car and two-wheeler, wheels. These are all, there are like this, there are so many examples of rotating masses, right? So what I tell is balancing of rotating masses, by which what is meant? There should be some imbalance in the rotating mass. That is why we are talking of balancing of rotating masses, right? So let us take the case of first one, ceiling fan, right? In the case of ceiling fan, normally 3 wings are there or blades are there. Let us assume one of the blade we are breaking it slightly, right? Rather, one of the blade is broken slightly, right? Then what will happen? The fan will not rotate about the vertical axis smoothly, and it will go on rotating, swaying like this, right? It will be swaying or as it rotates, or it will swing as it rotates, right? It will swing as it rotates. So what happened? There is now imbalance, right? That's why the fan is going on swaying like this as it is revolving as well. Instead of breaking the blade, let us assume we tie a bolt or nut at the end of only one wing. Then also the fan sways like this as it rotates, right? So why it happens? Now when the one wing is broken, or when a bolt is tied to one wing, there is an imbalance created in the system, right? Or the masses are not uniform around the shaft, motor shaft. This is what is happening, right? So to correct this, what we should do? The broken wing should be replaced by a new wing, just similar to the other 2 wings. Then when all the 3 wings are uniform, then once again without swaying, it rotates perfectly about the vertical axis, right? So when one bolt is tied to one wing, when we tie, if we tie two more bolts of the same length of thread to other two wings also, then also the fan rotates without swaying and rotates exactly aligned in the vertical axis, right? So like this. So when a bolt is tied to it or when a wing is broken, we have created an imbalance in the system, right? When a bolt is tied to a wing, there is a disturbing mass, right? Added disturbing mass. There is an additional disturbing mass. When one wing is broken, there is some absence of mass in one wing. That is a disturbing. That is absence of some mass. That is once again disturbing the system, right? So when there is some extra mass or there is some void or there is some absence of mass, it is called as a disturbing mass, right? This disturbing mass can be balanced by adding another mass at a convenient location or by removing some amount of mass at a convenient location, right? This is how the balancing of rotating masses are done, right? So if balancing has to be done, definitely there will be an imbalance, right? This is a simple example I told in the case of ceiling fan, right? But normally it will not happen in industrial rotating mass systems, right? For example, if we take a steam turbine, right? There are so many rows of blades in it, right? So in some row, in one blade, there might be some additional small amount of additional mass settled on the steam turbine, right? Or a small piece could have been broken, or a blowhole may be there in one of the blade, right? Even slight such change, the disturbing masses will include vibration in the system, because steam turbines or especially gas turbines and all, they run at 20 or 30 or 40,000 RPM, right? When they run at such high speeds, even a small imbalance will create severe vibration in the system, right? And you take the case of induced draft fan in the power plant, right? In the case of induced draft fan in the power plant, right, the ashes that are coming along with the flue gas, right, they, as we see, the ID fan or induced draft fan, draws the or pulls the flue gas from the furnace and it sends to the chimney, right? So as it does that way, the ash particles in the flue gas will go and which should pass through the impeller of the fan, right? So when it passes through the impeller of the fan, right, or when it passes through the impeller of the fan or rotor of the fan, the ash particles settle at some points, right, on the impeller itself, right? So this will act as disturbing masses, right? So when more amount of ashes are settled at those so many different places, the fan will start vibrating, right? So at that time, the ashes in the ash masses that is deposited on the impeller should be cleaned, right? Only then the fan will run once again smooth, right? These are all the examples of balancing of rotating masses, right? So now I will take the simplest case, right, where there is only one disturbing mass in a rotating in a rotor, right, in a single plane rotor, right, and I will tell you how it can be balanced. See, balancing of a single disturbing mass on a rotor of a single plane, right? This is the simplest case, right? Let us assume there is a rotor, right, like this, right, and this is a rotor, right, and this is the center point of the rotor, right. Let us assume some additional mass is there like this, right. Let the mass be small m, and it may be, let us assume it is located at a distance of r, right. So m is the disturbing mass, m is the disturbing mass, and r is distance of the distance of disturbing mass from axis. Right? This can be balanced by placing another mass exactly in the opposite direction, right? But it need not be placed at the same distance or it can be placed at some distance, right? Any convenient distance, and let the distance be r1, right? Let the distance be r1, and let this mass be m1, right? So the governing equation will be m1 r1 is equal to mr, right? So r1 is a convenient distance, and so balancing mass m1 is equal to mr divided by r1, right? So this is the governing equation, right? So what I will do, I will write what is m1. m1 is equal to balancing mass, right? And r1 is equal to distance of balancing mass from axis, right? This is the simplest example by which only one disturbing mass is there, and with another balancing mass on the same plane, right? It is a single plane rotor, right? Or very thin rotor, right? Or like a fan blades or something like that, right? In one plane, if it is there, right, it can be balanced like this. This is the simplest case possible. Let us see some fundamental of this disturbing mass now, right? Let us assume there is a rotor like this, as I told you, and there is a disturbing mass, let us assume, as shown earlier, like say m, right? This is your disturbing mass. M, right? And let us assume this is at a radius of r, right? R. So this is at a radius of r, right? Now let us assume this rotor is rotating at an angular velocity of omega, right? Angular velocity of rotor, is equal to omega radian per second, right? Okay, if that is the case, the centrifugal force created by disturbing mass, centrifugal force by disturbing mass is equal to m omega square r, right? This is your centrifugal force, right? So this centrifugal force, as I explained to you in the case of vibration, it will create a forced vibration in the system like this, periodic forced vibration in the system, right? So this centrifugal force, as it is acting, as it is going on rotating like this, and it is acting in a particular direction, it will create a forced vibration like this. Forced vibration. Periodic force, it will create a periodic forced vibration, right? So because of this, the system will vibrate, right? So when it goes to the top, it will be maximum. When it comes here down, it will be acting downwards in the maximum direction. When it comes here, it will act in the upward direction to the maximum extent, right? So it will try to pull the where it is mounted, if the rotor is mounted on a casing, it will try to pull up the casing and press the casing alternatively, right? And it will create vibration, right? and it will create a forced vibration like this, right? So this is the effect of disturbing mass. This disturbing mass will create unnecessary noise and vibration, right? Because of this, the life of the system, everything will be affected, right? And this is the fundamentals of fundamentals behind the disturbing mass and the effect of disturbing mass. And to balance it, what we do? Just opposite it, exactly opposite, as I explained in the other case, right? Just previously, with the help of by adding a balancing mass at a particular radius R1, we can just balance it, right? And the vibrations can be minimized or arrested, right? And now I will go to a little complicated case, a little more complicated case, right? So where in that case, let's assume the same rotor, a single plane rotor. Let's assume so a single plate rotor is there, and let us assume there are so many disturbing masses, right? So mass m1 is one disturbing mass, and mass m2 is another disturbing mass, right? Mass m3 is another disturbing mass. So many disturbing masses can be there. M1, M2, M3 are disturbing masses, right? Disturbing masses. In the earlier case, right, where there was only one disturbing mass, now there are so many disturbing masses. All these disturbing masses can be balanced by one single balancing mass kept at a convenient position, right? One single balancing mass can, this is balancing mass M, right? So here M1, M2 to M3 are disturbing masses, and balancing mass is M, right? And with the help of one single balancing mass, we can balance all, we can nullify the effect of all these disturbing masses, right? So balancing mass is equal to M, right? And this distance is R, right? So this is a little more complicated case, right? Now we will see another case where there are it's a longer. See, this is a single plane rotor. We will take the case of a big rotor mounted on a long axis, right? So on a long axis, so many impellers or so many. You take the case of steam turbine where there are so many row of blades placed over the axis through a longer axis, shaft, and in such cases, in each row of blade, there can be some disturbing mass, and so several disturbing masses in several planes are possible, right? All these things can be balanced by only two masses rotating at convenient planes, right? We can do that, right? Such a thing is the case where balancing of disturbing masses located in different planes, balancing of several masses rotating in different planes with the help of two balancing masses, right? That will be the extreme case, and that will be the ultimate case, right? So, case where balancing of several disturbing masses in many planes by two balancing masses, right? Now, that case I will draw it actually, right? It is like this. There can be a shaft like this, right? There can be a shaft like this, long shaft like this, as in the case of a steam turbine, right? As in the case of steam turbine. In the case of steam turbine, there will be two sets of blade arrangements, right? So from the center, right, about the center, symmetrically on both the sides, here impulse blades will be there, right? For to some extent, impulse blades will be there like this, right? Then a few rows of impulse blades will be there, and after that, intermediate stage blades will be there, like this. Actually, it will be going on increasing like this. Rotor blade diameter will be going on increasing as it goes away from the center. Okay, these will be intermediate stages, right? And finally, there will be diffuser stages, right? Diffusing blades, right? Diffuser blades. So it will be like this, right? It will be like this, right? Very symmetrically on the other side also symmetric mirror, like mirror image, so many blades will be there, right? So on this side also to be there, right? So diffuser blades will be there. So these will be intermediate stages like this. It will be like this. The same number of blades will be there on both the sides. 3 plus 3 is 6 plus 4. So like this, 1, 2, 3. How many sets of blades are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If 10 blades are there in this side. This side also 10 blades will be there. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. We will put one more, right? So here also 10 blades are there, right? So steam turbine will be at the center. See, some impulse stages will be there. These are called impulse stages. Impulse stage. Then there will be some intermediate pressure stage, or here this area is low pressure or low pressure stages. This is low pressure stage, whereas this is intermediate pressure. This is sorry, this is not low pressure. I'm sorry. Yes, low pressure stages. Low pressure stages, intermediate pressure, intermediate pressure stages, and these are impulse stages, which are high velocity stages. High velocity stage. Impulse stage is called as high velocity stage. Here, the jet of steam turbine will be introduced at the center, and the steam will be traveling both sides like this, right? Steam will be traveling both sides like this. So it will be introduced at the center, and it will get divided, and it will flow like this, right? So as it is starts flowing here only, the high velocity will be here, and as it goes on to the end, velocity will be continuously decreasing, and here why it is called low pressure, because at this end, this end will be connected to condenser, where there will be a vacuum pump, and it will be trying to pull the steam. So here low pressure will be there, right? So here at high pressure steam will be injected, and as it comes out of a jet of nozzle, as it comes out of a nozzle, all the high pressure will be converted as very high velocity, and so it will come as high velocity steam at this end, and goes on, the steam velocity will go on reducing here. At the same time, pressure also will be reducing, right? Because at this end it will be connected to a vacuum pump that will pull the steam through the condenser, right? So like this, there are so many stages like this, right? And one disturbing mass can be in this stage, one disturbing mass can be in this stage, two disturbing masses can be here, one disturbing mass can be here, like this, in so many different planes, right? There may be so many different disturbing masses, right? And steam turbine and all are rotating at 3000 RPM, right? and earlier the steam turbine were used to run at 6000 RPM like that, right? So now they have made the design in such a way that the generator and the steam turbine are having the same RPM of the 3000, because in order to avoid the gearbox, right? So nowadays steam turbines are designed for 3000 RPM, right? Whereas small turbines and all are designed for 6000 RPM, something like that, right? So industrial turbines are designed for 6000 RPM like that, right? So when it is running at such high RPM, right, and even a small disturbing mass, right, and see there are the blade, so many blades in each row. This is each one. See, each one stage is nothing but a row of blades, right? So the blades are like fan blades. So many blades. Fan blades are only 3, whereas here so many number of blades will be there in one plane, right? So like that, thousands, hundreds and thousands of blades will be there, right, on both sides of the rotor, right? So there can be any disturbing mass anywhere, right? So all these disturbing masses can be balanced by in total by two. All these disturbing masses can be balanced by two balancing masses conveniently located at any particular stage of the blades, right? So like this, it is possible, right? This will be the extreme case or ultimate case where balancing is very, very difficult and it is generally done on a computer, right? So normally, if you take the car wheels, right, all of you would have seen balancing of car wheels in workshops, right? In the case of balancing of car wheels, you would have seen small masses inserted between the tire and the wheel rim, right? So here, there also the wheel will be kept over a shaft and it will be made to run, and the computer will say how much amount of mass to be added at the wheel rim and in which plane, right? Where they will insert it and hammer it slightly, right? And that will give you the balancing of the wheel, right? So when there is complete balance, the vibrations will be minimum and unnecessary noise, everything will be minimum, and once the vibrations are minimum, the life of the rotor also will be more, right? Thank you.